this is striped order in AdS CFT. This is based on these two papers with our postdoc Evgeny Sorkin, who just left actually, and two excellent students, my student Darren and Mark's student Jared. The short version of that appeared in this paper, and then there was a long version with all the gory detail. Now, since I come after Jerome, I have to, I can be brief about the introduction, but let me tell you a little bit about my motivation. So first of all, stripes are known, stripes, or as Jerome said, other inhomogeneous structures are known to form in many strongly coupled systems. They also are very unusual in weakly coupled systems, and therefore in holography it's a natural thing to look at or to be interested in. And the earliest interest that I personally had in that is in the context of large NQCD. So it's known that asymptotically large chemical potential, there is some instability to forming a chiral density wave in which the chiral condensate develops some modulation. It is an asymptotically large chemical potential, but nevertheless, in holography, where you usually work in infinite n, you ought to be able to see that. And later, I also discovered that this is actually a fairly generic phenomena in phase diagrams of strongly interacting materials. There's usually some part of the phase diagram in which all kind of inhomogeneous order is manifest. So this is something to be interested in. And it might be just that strongly coupled systems are very complicated and therefore they have unusual properties, but at least there is some indication that this is important in some, at least theoretical speculations. And what I'm going to do about in this particular talk is talk about one specific example in which we constructed an inhomogeneous black hole that is dual to a state which breaks spontaneously the translation invariance in one direction. One of the points that I'd like to make later is that there's probably many such examples, and it's interesting to look and compare and contrast different examples that exist. Let me just, in a way of motivation, talk about other reasons to be interested in spatial inhomogeneity in the holographic context. I'll be brief here because many of the other talks talk about similar things. So there's two nice papers by Aristos and Sean that talk about use of inhomogeneities in order to discover interesting physics. There's, of course, the scaling laws that are discovered once you add a lattice, or spatial inhomogeneity once you source the theory in some inhomogeneous way. Let me also discuss this interesting physics that can happen in an interface between a topological material and a non-topological material. Usually most interesting physics there is at the edge, and obviously you cannot discover it if you don't discuss spatial inhomogeneity. So this is an example of my recent paper. One more example of people in the audience. So it's part of a general program of understanding holography in a more generic way, in which a lot of new physics is coming about. Let me also say that especially inhomogeneous solutions are interesting from the gravity side, not just from the field theory side, because they bring about new issues and they result in new type of black holes, new type of Einstein equations. It's also that usually you have to study those things numerically, and the numerical methods are very well developed. So normally you don't have to reinvent anything. The numerical methods were developed for you. So this could be a motivation to get into the subject. So let me explain or discuss or summarize what what we've done, and kind of to avoid confusion, how is that compared to other types of work. So as Jerome reviewed, there's a lot of work on discovering linearized instabilities which have some spatial modulation. They have non-zero wave number. So at some point in the phase diagram, you develop a zero mode, which would then become tachyonic as you cool down the system. And that tachyon has non-zero wave number. So there's a lot of examples of that. Now, there's a lot of examples of perturbative solution in which the scale, the amplitude of the inhomogeneity is small. So you do perturbation theory normally to first or second order. So for example, there's the work that I cited about vertical lattice is done in that way, and that's an interesting thing to do, but it's valid only in a certain part of the phase diagram, typically near the phase transition point. And some back-reacted solution exists with source inhomogeneity. So this is the work, for example, of the holographic lattices. In most such cases, the inhomogeneity is irrelevant. You source by any relevant operator. It means that the scale of inhomogeneity is large near the boundary. It becomes smaller and smaller in the infrared or near the black hole horizon. As we'll see, we have kind of the opposite kind of black hole. And there's some new issues, some technical issues and some conceptual issues to do with the fact that things grow towards the infrared. And as Jerome just talked about, there are some interesting solutions. They require special tricks. So in order to reduce the problem to ODEs, there is some extra symmetry. The solutions are inhomogeneous, but nevertheless you can solve them simply. So there's a lot of nice work along those lines. So to contrast or to explain what we've done, so we construct a nonlinear solution. It requires solving PDEs, so therefore it is cohomogeneity 2. We unfortunately could not go to ODEs. It's a static solution, so it's if you want a saddle point of it's described a particular phase at finite temperature, and that phase breaks spontaneously translation invariance. And as I'll emphasize later, this is a specific solution. In many ways, we'll see that it's a very special solution. And one thing that would be nice to explore in the future is all the different kinds of strike phases that exist and what's the difference between them. Okay, so that was a brief introduction. This is my outline. I'm going to talk about the instability that was discovered by Aristos and Jerome. Then I'm going to talk a little bit about the geometry, the bulk geometry. It has some unusual features, which I think are interesting. And then I'll describe the thermodynamics of the system and conclude. Okay. Good. So the model is along the lines of what Jerome just explained. In fact, he showed that model. So this is the AdS for Einstein-Maxwell theory, which is used for many purposes. Here we have a neutral scalar, so there's no charge fields. And we use m squared equal minus 2, which is convenient for various reasons. And the only unusual feature of this model is this coupling. So this is a coupling of an axion-like field, that neutral scalar, with couples to this topological density FF dual. And that's kind of the interesting coupling that drives everything in this system. And it's very interesting, this is the bulk side of things, that this is axion electrodynamics. And in fact, as we'll see, a lot of the features of this solution could be understood from this point of view. Axion electrodynamics arises in the boundary side, or in a field theory side, as an effective field theory that describes the coupling of electromagnetic fields to a topological insulator. And in particular, as I said before, the interesting thing in that context is that the topological insulator can have interesting phenomena occurring on their boundaries. Okay. Good. Okay, so what we're going to see, and the reason why this is a nice way to think about that, is that in addition to having this axion electrodynamics, we're also going to have spatial modulation. So we're going to have something that models an interface between topological and non-topological insulator, but in the bulk now. And as familiar from the condensed matter side, this will result in what's called the magnetoelectric effect. Again, this time in the bulk, which is familiar with the study of topological insulators. Okay. So this is a nice way to gain some intuition about what happens in the bulk geometry. Good. So this model was studied by, again, Aristos and Jerome, and they found an unstable mode of finite wave number at some critical temperature. There's a highest critical temperature for the specific wave number, and of course there is a range of wave numbers that are also unstable. And what we've done here is to follow the branch of new solution that develops as you lower the temperature and follow this maximal or the dominant tachyon. Now, one thing that you can vary in this is there is this one coupling which drives the instability and all the interesting physics, and as we'll see, changing this will change the magnitude of all the instabilities in this geometry. So this is axion coupling C1. So at this level, as you increase C1, then that results in higher critical temperature and higher critical wave number. So all the regions, so this is C1 equals 36, the region under this curve is all unstable. Compare that to C1 4.5, which is the lowest thing I'm plotting, the region of instability is much smaller. And that's intuitive. Okay. The other thing about the linearized analysis, which is useful to know, is what mode becomes unstable, and that mode has that axion, so that axion field with this particular wave number. But in addition, and this is something that, again, you can understand the analogy to the topological insulator, it develops a current in the y direction. So we're breaking translation invariance in one direction, which I can call x, and the current flows in the perpendicular direction. There's also momentum in the y direction, which is intuitive, and all of those fields are modulated with the same modulation in the x direction. Okay. Now, once you turn on nonlinearities, then you have other fields of the bulk that turn on because of the specific structure of the perturbation. Those actually have a different modulation. They have twice the wave number, and as we'll see, all of those fields, as we cool down the system, acquire very significant modulation near the horizon. Okay, let me flash a quick, I don't have much time, so I'm not going to go over the details here, but just the technicalities. So here is a set of choices of how to set up the problem, then how to discretize it, and then how to solve those discretized equations. Now, this is not a unique set of choices. It might not be the best set of choices. In fact, there's nice work by Aristos and by Ben Withers that use other methods. But as I said before, all of this is well understood and well developed. So this is just summarize all the choices we made, and of course this is all in the longer version of the paper. Okay, so this is the instability that we're going to follow. So we solved those equations numerically, and here are some features. So the first thing to look at, and the thing that is most intuitive, is the boundary observable. So the boundary observable I read off the usual way by looking at the expansion near the boundary and extracting the subleading terms. So as I said, the boundary theory exhibits spontaneous breaking of translation invariance. That means that all the non-normalizable modes are completely homogeneous. It's only the normalizable modes that develop those modulation. Okay, so in particular, this scalar field is modulated. It acquires a VEV. Now, there's also modulation in these two fields. It means that there's both charge density waves and current density wave in this particular model. And there is some relation between their modulations. There's also modulation in those energy momentum tensor components. Well, this is the energy density, and this is the pressure, and there's also a non-zero momentum in the boundary. The momentum flows in the y direction, exactly like in the reiterative treatment. And by virtue of conservation, we only break translation invariance in one direction, so everything depends only on x. Then the derivative of dxx should be 0. So this particular quantity should be homogeneous, even though everything else is non-homogeneous. And this is actually a very good check on the numerics. And the other thing to say is that we look at it as a function of temperature. As you lower the temperature, then initially, as you go below the critical point, all those amplitudes of those modulated quantities, they become larger and larger with decreasing temperature, but they all saturate. So there seems to be a finite limit as you go to t equals 0. Okay. Good. So some qualitative feature of the geometry. So we, for technical reason, we constructed solution at finite temperature, starting with the critical temperature and lowering it down. We did not construct the solution at strictly 0 temperature. That's difficult. But we went to temperature, which is roughly 10 to the minus 3 times the critical temperature. And these figures are for these values of parameter, temperature, which is fairly cold. And the modulation, as we see in all these fields, the modulation grows towards the horizon, and everything is normalizable at infinity. There is some staggering of the periodicity. Some fields have twice the periodicity of others. And let me highlight that there is an interesting thing to do with the field AY. This corresponds in the bulk to an existence of magnetic field near the horizon. And this magnetic field near the horizon is also accompanied by some rotation. And all of this, as a function of temperature, grows. All this structure becomes larger and larger as we cool down the system. So as we saw, the inhomogeneity as is expressed by boundary observable saturates as you go to lower temperature, but that's not true for the bulk geometry. The bulk geometry actually becomes more and more pronounced near the horizon. So there's some discussion about that later. So a lot of the bulk geometry could be understood with this analogy with this topological insulator, and in particular this magnetoelectric effect. So in topological insulator interface, which is sort of mechanically similar to the configuration we have here, what we have is that a gradient of the axion induces a current in the perpendicular direction. Now we have an axion which is modulated, so therefore there is gradients. There are gradients. You can think about that maybe as a domain wall, anti-domain wall periodic structure in one direction. And therefore there's going to be current which is localized at those interfaces. The electric field is supplied by the Reissner-Nordstrom black hole, it points in the radial direction, and all of that results in electrical current in the bulk that moves in the y direction. Okay. Once you understand that, then all the features of the geometry become clear. For example, this current in the y direction results in a magnetic field, and the magnetic field, once it's coupled to gravity, results in some vorticity. This vorticity, I should say, this is a minor point, but there's no ergosphere here, even though there's notation in this geometry. Okay. So this is another way to demonstrate the same point. So this is the metric function GTY, which corresponds in the boundary to the existence of momentum flow. And what it shows in the bulk is, so in this plot, the right is going to be infinity, the left is going to be the horizon, and what we see here, there's two regions of counter-rotating matter. It's localized at some point near the horizon, but it's not a feature of the horizon itself. And so this is an example of a black hole which is by itself not rotating, but which has some rotation in the geometry. So it's stationary, but it's non-rotating. Okay. So let me just make a quick comment here. So there is some kind of resemblance to topological order in the bulk here, not in the boundary. And in this particular case, this seems to be an interesting or an important part of the story. In fact, that's the part that drives the instability. Now, as we heard, there are other examples in which you don't need those axioms or those breaking of P and T invariance, and it would be nice to understand what drives the instability in that case. Okay. Okay. So another feature of the geometry that's interesting to look at is the following. So as I said, at the lower temperature limit, all the boundary observers saturate to some finite values, but the geometry develops some pronounced features. So some of them are mild. For example, the Ricci scalar at the horizon does not diverge. It just increases, but then saturates as we lower the temperature with T equals 0. But what happens, one thing that does diverge is the following. So if you think about the proper length in the inhomogeneous direction, that is something that starts out at some period at infinity, and then it increases towards the horizon. And at every finite temperature, that increase towards the horizon saturates at some maximum. So the value of the periodicity at the horizon is always larger than the value at infinity. That value at the horizon diverges. It diverges fairly mildly as a function of temperature, but nevertheless, it looks like the horizon becomes infinitely large at the zero temperature limit in the x direction. On the other hand, you can think about the transverse direction. So the transverse direction is modulated. This is summarized by the metric function gyy, and it
So you just mentioned that the horizon becomes translation environment in the zero temperature limit?
No, it's still modulated. It's just that the length, the proper length, becomes infinite. So if you want the proper modulation, it becomes zero. I'm not sure how to quantify that. The proper length in the x direction diverges in the zero temperature.
And the horizon is also at infinite proper distance away, right? In that case?
No. Oh, okay. No, I don't think so. I don't think so. That's related to this. No, I don't think so.
Right, and this rotation step lifts away from the horizon.
The rotation is away from the horizon. Yeah. So these are independent features. Those are features. So there are features of the geometry, which is an interesting point. I think there are features of the geometry that are localized at some finite radius, but have nothing to do with the horizon. but those are features of the horizons. The other interesting feature is that there is geometry at the horizon as a point of minimum GYY or minimum size in the y direction and a maximum one, and their ratio becomes 0 in the low temperature limit. So it looks like basically the horizon is pinching off. Now the reason why we went through this is, again, we didn't construct the t equals 0 solution, and those are hints of what the 0 temperature solution would look like. So the ground state here looks like it's going to be pinching off. It's going to be infinitely large, so it looks like a reasonable guess is that there's going to be an array of lower dimensional structures that are localized in the x direction. Okay. And this is what happens in the Gregory-Laflamme story. Okay, questions? Okay, so the last thing to talk about is the thermodynamics. So we looked at the thermodynamics in various ensembles. So first, what we did is we followed the instability at the highest critical temperature, and we focused on this particular mode that becomes stable. Later, we're going to compare different modes with different wave numbers. But the first analysis is just discuss that critical mode. So in order to do that, we fixed the asymptotic length of the system to be 2 pi over that critical wave number. And in the canonical ensemble, we construct the free energy as a function of temperature. Because of conformal invariance, things depend only on the temperature over the other thing that you keep fixed here, which is the charge. And we find that there is a second order first transition in that critical temperature that was found by the linearized analysis, meaning that those stripes dominate right away, just below the critical temperature. As you cool down, the stripes become more and more and more dominant. So this is the picture of a second order phase transition. Now we also looked at critical exponents. So we looked at free energy in particular, and we got the expected critical exponents. We also looked at this system, but fixed the length to be 2 pi over other wave numbers, other critical wave numbers, and we find fairly similar results. So it looks like basically all of those wave numbers become unstable and dominate the thermodynamics below their corresponding critical temperature. Okay. Now, we did all of that as a function of C1. So C1 was the axion coupling. For larger axion coupling, everything is more pronounced. So there is a very clear phase transition in the higher values of C1. This is C1 equal 8. As you lower C1, there is a point where these two curves becomes almost degenerate, and within the accuracy of the numerics, it looks like if you lower C1 further, the phase transition is going to disappear. Okay. Now we looked at this system in other ensembles. So for example, you can fix the temperature and the chemical potential. So we also found, not surprisingly, the same type of phase transition. The other thing that we can do in this system is to look at some critical exponent for other observables, not just the free energy. So in particular, you have those following critical exponents just below the critical temperature for the momentum density, the scalar condensate, and the current density, and they're all kind of more or less 0.4 with errors within 10%. So they seem to be deviating from expectation from mean field theory. Okay.
So I get it right that the axial field is really driving the phase transitions, and these others are more like parasitic following it.
Sorry?
It is basically by the nature of the phase transition, right? So there are these different paths you develop.
So this is for one of them. So I'm fixing.
Yeah, just a very general question.
Yeah. Yeah.
A typical way to think about it is that there's one dominating order parameter that
Yeah.
reduces parasitically all these other paths. And I guess that's like
Yeah, so the way the way to think about that, or maybe one way to think about that, is that action field drives everything else.
Yeah.
Once you understand that the action field has developed spatial modulation, all the other features that I'm discussing are going to follow intuitively from that.
And an action field is doing a mean field, and these other parasitic paths.
No, I mean all of those exponents are fairly close to each other, definitely within our numerical errors here. So it's 0.4.
I just try to get a picture, right? So you said before it's like a mean field position.
Well, before
refers to the axial.
the free energy has a mean field exponent, but we're now looking at other kind of observables, and they seem to have, yeah.
So there is no consistent perturbative way of thinking about this?
You mean perturbative way in what?
I mean, perturbation theory has to somehow break down there, if you find such exponent.
Well, yeah.
Is there a lambda theory for it? There should be a lambda theory in principle, and the students are
There should be a lambda theory in principle. I'm a little unclear what the lambda theory looks like for inhomogeneous order parameters. So, for example, can I just think right away of what the critical exponent is if the order parameter is inhomogeneous?
You know something about liquid? That's a
So it's a different type of. So maybe this there is no difference. So there should be no difference if the order parameter. So it's the same. You just have a theory for the order parameter. Yeah. Yeah. Okay. Yeah. Well, the boundary interpretation of this theory, as you know, is a little mysterious. I don't know which theory it describes, but presumably, if you're asking about the perturbation theory in that frame.
I mean, just by solving the equations of motion of gravity, to me, I think it should be mean field.
This is a general statement about holographic theories.
Yeah, in principle they are mean field theories, so it's strange that you can get non-mean field exponents. But
Okay. Okay.
because with large n, you are killing off fluctuation in principle, right? So,
Okay. Yeah. 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 Okay. So yeah, let me think about that. Okay. So again, we looked at the thermodynamics in different ensembles. The only interesting thing in this microcanonical ensemble is the following. So you have inhomogeneous solution. They start dominating the thermodynamics right away below the critical temperature. The interesting thing here is that, of course, in this ensemble, the homogeneous solution only exists for mass which is sufficiently large because of the extremality bound, whereas those inhomogeneous phases continue going down below that bound. So here, below a certain threshold, there's only inhomogeneous solutions which have higher entropy. Okay. The other interesting thing to look at, which relates to something Jerome said, is so it's interesting to see what happens here at zero temperature, whether you have a ground state entropy or you don't. And that's a little bit tricky question to determine numerically. Within the uncertainty of our numeric, it does look like you do get a finite value of the entropy at zero temperature, but again, there's some extrapolation involved here. In the sense, sometimes the ground state entropy falls to zero fairly quickly. So, in which case we won't be able to see that. But that's just an interesting feature. Okay. Finally, as I said, in the infinite system, if you don't fix the periodicity, then you are in a position to compare the free energy of all those different stripes and see which one of them dominates as a function of temperature. And what we see here is the dominant stripe increases as a function of temperature. We start with the critical wave number at the highest critical temperature, but then steadily it increases, and it approaches a period which is roughly twice that of the initial period. Okay. All the other results are qualitatively similar to the finite system. Okay, so I'm almost out of time, so let me summarize. So there's some more things to do here in the on the stripe front. First of all, the obvious thing to look at is the ground state. So we have some kind of intuition what the system looks like at lower and lower temperature, what is the gravity solution tending to as you lower the temperature, and that hopefully will allow us to have some ansatz and check that. In particular, what is the infrared physics in the ground state. Now, it's interesting to see what the interplay here that you have between inhomogeneity and topological order in the bulk. What does that tell you about the boundary? And there might be more general context in which this is important. Now, another thing that I mentioned during the talk is so this is one particular example of a stripe. There is a whole zoo of those things, and it's interesting to start not classifying them, but at least understanding what are the differences between different stripes. Here, it seems like the stripe formation is very closely related to those axion terms and those kind of analogy to topological order in the bulk, but as we heard, there are other examples where those terms are absent, and therefore presumably some of the features of geometry are going to be very different. So the question is the physics in that case very different? There ought to be different mechanisms or different ways of generating inhomogeneity, and it's interesting to look at different examples to start understanding what is the space of possibilities there. Now, the other obvious thing to do is, to look at transport coefficients here and maybe identify scaling laws or maybe identify other interesting features that you get with sourced inhomogeneity. Here, the inhomogeneity comes spontaneously, but there should be some similarity, except here the inhomogeneity, because it's not sourced, is associated with the infrared physics rather than the ultraviolet physics. Okay. Let me end here. Well, I think I'll leave that.
Yeah.
Have you already tried to look at the Goldstone bosons? I mean, I'm really intrigued by this form of order. When you look at the Goldstone bosons, I guess you get more idea of exactly what the order is. Right? It shouldn't be like simple phonons. Okay?
So the Goldstone boson here probably is going to be seen by fluctuations or by Green's function of that axion, I would think. But
I don't know. We have more symmetries in the game, right?
well, I mean, if you calculate 2-point functions of most operators, you're going to get a Goldstone pole. But I'm thinking the axion operator is the one that naturally couples to that.
Oh yeah, so you break, it's one translation, right?
Yes.
So they would have one phonon. But I think there's a lot more there. That's actually the question. How you get more idea about what?
Yeah, there should be phonons corresponding to the broken translation in the x direction.
Look forward to get an analysis of that.
Yeah.
Any further questions? None. Let us thank Moshe again.